Yeah, okay. You are screen sharing. I'm assuming I'm recording. Yes, you got a button. Okay. So we are talking about one-way ANOVAs, and then next week will be one-way ANOVA advanced, so mandatory for only the PhD students. And then there'll be an assignment due that Saturday. So for the master students in the class today, you'll know everything everything you'll need for the assignment, and it's due not this Saturday, but next Saturday. And then we're going to do factorial ANOVAs, again, 2 weeks. Then we'll do repeated measure ANOVAs with the typical, again, 2 weeks. And then we'll be done. There's no final exam or final assignment. Your grades will just be as detailed in the course syllabus based on your in-class assignments and your at-home assignments. So there's, I guess, 3 more I guess it depends. Master students, so it'll be 3 more in class, 3 more at home. PhD students have 6 more in class and 3 more at home. Questions on our schedule? So it'd be good to touch base after our week off where we are. The assignments were generally done well, which was good to see. One thing, well, some of the confidence intervals sometimes were fine. Sometimes they weren't perfect. Usually the ones that you can pull of SPSS were easier, especially if you just pull them right out. So your standard 95% confidence intervals and the mean difference and its confidence interval, because you can pull it out of SPSS. The difference adjusted sometimes we're wrong, so we'll practice those again today, and you will see them on the in-class and at-home assignment. So if in your assignment you got it wrong, you can't quite figure out, hopefully I gave you the right numbers for at least some of them. Then feel free to work on that and talk to me so you got them down pat. The other thing that I saw quite a few mistakes on, probably more often incorrectly done or maybe not perfectly done, were tests of normality. And that's when we look at the KS and SW tests. But it's more complicated than just, is it significant or not significant? So if it's significant, that's bad. Often a significant result is good, but if this test is significant, it says there's a departure from normality. But the underlying layer is, well, how many participants do you have in that group specifically? So if you have 30, then it kind of doesn't fall into either category, and I guess it's a perfect test. I don't know if it's safe to assume that or not. But if you have less than 30, those tests for normality are underpowered. So even if it's not significant, you can't 100% say that they are normally distributed, because maybe your test is underpowered. It just doesn't have the power to detect a departure. So in that case, you should say, hey, it could be one of 2 things. If you have a large sample size, then if it's significant, either KS or SW test, the complicated situation is, well, it could be a departure from normality, the test is significant, or the test could be significant because it's overpowered, which is the opposite problem we saw here. So if you end up in that area, then there's 2 possible conclusions. So there's 4 cases. It could be here, 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 or here. In these 2, there's a definite answer. In these 2, you're left not knowing what the exact answer is. I think there are many people who might have received 0.5 out of 1. I didn't take off a mark if you said they're significant, but you didn't say they're also overpowered, because the conclusion is still they're significant. But if you fell into one of these 2 categories on the assignment, then I did want you to say, hey, we don't know if it's this case or that case. Any questions about that? That one. All right, one-way notes. We got too many screens here. Hopefully no one else joins and I don't let them in. Hopefully Marianne can hear us. So we're going to talk about one-way ANOVA, kind of typical outline we've seen in the other sections, but we're going to start with the justification for why. why do we need a one-way ANOVA? And it's related to the family-wise error rate. The puppy therapy examples from the textbook, we'll look at that as just a quick running of a one-way ANOVA. I always like to try to do it before we talk for an hour without even running the test. We'll talk about effect size, which we're going to need to use eta squared instead of colons d. Because it's a similar measurement, but it's what's used for one-way ANOVAs. Then I have a VO2Max example that I made up where we'll kind of go through all the assumptions and look at post-hoc comparisons and what we do with the manuscript. So we'll spend most of our time here giving a full treatment for this example. So has anyone heard of the Familywise error rate?
It's words. It's right there.
That's good. Yeah, sometimes abbreviated FWER. That's a good start. So here I tried to depict it in pictures here. So let's say we've got two groups, and we'll stick with the well, we could use a t-test for this. It would be an independent samples t-test because it's two different groups. One group comes in, they take a control, and we test their blood pressure. Tell us about blood pressure or vasodilation, something like that, right?
Yeah.
I guess if you're better dilation, you might have better blood pressure.
Yeah.
Okay. I'm ready for Arun's. In case you haven't heard, Arun is defending on Wednesday his dissertation, and he was one of 3 students in our first batch of PhD students, and then Haley is actually defending on Thursday. Okay, and then another group takes L-citrulline, and we want to see, who has better vasodilation. We can compare them with the t-test. That's a pretty simple experiment, and it doesn't take long until our experiments get a little more complicated and we get out of t-test territory or 2-group territory. So one t-test to compare these 2 groups. But now let's imagine you're a little more curious about how L-citrulline works. You're like, oh, is there a dose response? Does it matter if you take a low dose or a high dose? So we add in a 3rd group. We've got 3 independent groups. And you're now wondering, well, how do I analyze this data? The answer is one way ANOVA. But you might be thinking, could I just use multiple t-tests? So how many t-tests would we need? Well, we might want to compare control to low. This would be if we want to make every possible comparison. We call that full pairwise comparisons. So we say, okay, we might want to compare those 2 groups. Those 2 groups. Over here. There we go. Sorry, Mary. and then those 2 groups. So those are the 3 possible pairwise comparisons in here. So we could do that with 3 t-tests. The challenge is that each one of those t-tests has a 5% chance of a false positive. So typically we like all of the tests together to have a 5% chance of a false positive. But if we do 3 tests, then that it's no longer going to be 5%. It's going to be higher than 5%. We'll look at the math in just a second. And that increase in what we call like the effective alpha is what we refer to as the Familywise error rate. So we like that to be for all tests, and it doesn't really work out that way. We'll talk more about that with factorial ANOVAs to be 5% chance of making a mistake in the whole experiment, sort of, not in just the individual statistical test. And here, if we did 3 t-tests, the effective alpha or the Familywise error rate would not be 5%, it would be higher. And that's why we don't do multiple t-tests. We do a one-way ANOVA, and within the one-way ANOVA, it controls the Familywise error rate for the effective alpha to be exactly 5%, or a touch lower. So to look at what is the probability of a false positive with 3 t-tests in this example, and you could imagine an experiment with 4 groups or 5 groups, and the Familywise error rate or the chance of a false positive would keep increasing to be more and more likely. So to look at that, we need to remember that there's three possible outcomes from a statistical test, but we're going to focus on the assumption that in reality, there's no significant difference. So in that case, your test is either going to be a true negative, which is good, and the chances of that happening is 1 minus alpha, where alpha is typically 5%, so probability of a true negative in one t-test is 95%, and the possibility of a false positive is a probability of alpha, or 5%. And we have to set that line in the sand that false positives are going to occur even when we know that in that reality there's no significant difference. But what happens when we do multiple tests? Or, well, actually, let's look at just one test first. So the way I would write that in numbers, the chances of true negatives and false positives would be like this. So I'd say the possible outcomes of a single t-test is either a true negative or a false positive. And the probability of a true negative is 1 minus alpha, and false positive is alpha. Alpha is typically 0.05, so we'll throw those numbers in. And those, of course, should add up to 1. It's 100%. So here with the t-test, yes, the chance of a false positive is 5%. What if we have 3 groups and we decide to do 3 t-tests, to do all possible pairwise comparisons? What's the probability of a false positive here? And we also call that the family-wise error rate. So here, all possible outcomes, they need to add up to 1 or 100%. And this is what can happen. The most likely thing that would happen is that we get 3 true negatives. And the probability of that happening for the first test is 95%, 1 minus alpha. For the second test is 95%, and the third test is 95%. Another possible outcome is that the first test we get a false positive and then 2 true negatives. And that would be for the first test. We could have a false positive for the second test, and true negatives, or we could have a false positive for the third test, the first, second, and true negatives. We could have 2 false positives, not as likely, but we could have 2 false positives and 1 true negative. And those 2 false positives could be the first 2 tests, first and the third, or the second and the third. And then the least likely outcome, but it could still happen, is that you have 3 false positives. So we take alpha, multiply it, by itself 3 times. So that's quite unlikely, but it could happen. So if we look at those numbers, all I've done is just multiplied each section. So the probability of 3 false positives is very, very small. But and then the most likely outcome is 3 true negatives, far more likely. So here what I've done is I've grouped some together. So that first one, that's the probability of 3 true negatives. So all good results. Here's the probability of 1 false positive, could be test 1, test 2, or test 3. Here's the probability of 2 false positives, so less likely, but could happen. And this is the unlikely or least likely probability of 3 false positives. And when we add those all together, we get 1. And I've used excessive digits here, so that I think it hopefully adds up to 1. If you round it too much, it might not be exactly 1. So, and then in this line, what we have here is, this is the probability of 3 true negatives with results. This is the probability of 1 or more false positives. So it's this plus this plus this. So it could be 1 false positive, 2 false positives, or 3 false positives. And this is the effective alpha. So if we did 3 t-tests, the probability of at least 1 false positive is not 5% like we would like it to be. It's about 14%. So this is the effective alpha, or we can also call it the family-wise error rate. Because we've done 3 t-tests, each with an alpha of 5%, the effective alpha or the family-wise error rate is not 5%, it's much higher, 14%. Now, if you'd like to calculate, oh, so yeah, there we go. There's our family-wise error rate. Did I duplicate that slide? If you want to calculate the family-wise error rate, instead of having to go through all of this, what we can do is we can say, hey, 1 minus the probability of all true negatives will equal the family-wise error rate. So just rearrange that last line. And the more generalized form for this equation is, remember how we got this? We took 1 minus alpha and multiplied it by the number of t-tests. So in other words, 1 minus alpha times the number of t-tests. That will give you your family-wise error rate. And if you had 4 groups, we'll look at that next, you have to figure out how many comparisons there are with 4 groups. You plug that number in here and you calculate the family-wise error rate with 4 groups or 5 or 6. And you'll see it increases rather, again, well, is it fair to say exponentially? Larger, there's a larger increase than linear. We'll see a graph in a moment. Okay, so here's 4 groups. So let's try that formula. The first thing we need to do is find out how many comparisons there are with 4 groups. So how many unique 2-group comparisons, or how many t-tests could we use here? So we got 1, 2, 3, 4, 5, 6. And the formula for that is K as in the number of groups. So K, the number of groups. 4 conditions if it were a paired sample t-test. Groups. And then to find out the number of comparisons, it's K multiplied by P minus 1 divided by 2. So in our last example, remember we had 3 groups. So 3 times 3 minus 1 divided by 2, 6 divided by 2, which is 3. And remember we saw previously we had 3 comparisons. Here it's 4, so 4 minus 1, that's 4 times 3, which is 12, 6. It matches what we see in our diagram. And that, I mean, with only 4 groups, it's not too hard to count them, but the higher you get, the more handy that formula is. So what's the family-wise error rate here? Or in other words, what's the probability of at least 1 false positive? Well, we're going to use this formula. And here we're going to put the number of comparisons, which is 6. And we'll ask PowerPoint to crunch those numbers. And we can see it's 26%. So if you did analyze these 4 groups with 6 t-tests, there's not a 5% chance of making a false positive. There's a 26% chance of a false positive. And generally, the higher the family-wise error rate, the more uncomfortable we should get that we're making a mistake. And here's a graph that shows the family-wise error rate based on the number of groups. I kind of debated whether I should plot number of groups or number of comparisons, because with 2 groups, there's 1 comparison. With 3 groups, there were 3 comparisons. With 4 groups, there are 6. So it kind of depends how you think about it. But you can see the family-wise error rate. And one thing I like to look at is, okay, well, when is there a 50% chance of making a mistake? It's around 5 groups. So it doesn't take very long until you're likely to make a mistake. And I mean, you had 10 groups, you've got like a 90% chance of making a false positive. That's not good. So what do we do? Well, instead of doing just multiple t-tests, which we will come back to that because that's kind of like what post-hoc tests are. But we're going to do an initial test. We're going to use a one-way ANOVA, which is a statistical test designed for comparing multiple groups or more than 2. So you can compare 3 groups, or I don't think SPSS will do 100. I think it will actually do 99. But at that point, it's a little silly anyway. And the fun thing about a one-way ANOVA is it controls the family-wise error rate or the effective alpha, so that it is 5% or whatever you set your alpha to, regardless of the number of groups. So if you have 3 groups, your family-wise error rate is 5%. If you have 4 groups, 5%. If you have 6 groups, it's 5%. will always be 5%. It makes the appropriate mathematical calculation to control the Familywise error rate to 5%. And we'll see how that's done. Well, on a surface level, we won't play with the math. We will see a little bit in the advanced class. We'll come to this a little later, but this is also the case for orthogonal contrasts, or what are called a priori comparisons. We'll leave that for the advanced class. We will talk about post-hoc comparisons later today, where the Familywise error rate, something needs to be done in it to control it. Because the ANOVA control is linked to the ANOVA. We're going to need post-hoc comparisons, and then we'll need to consider the Familywise error rate again there. We'll see why that's necessary soon. Any questions on the reason why we need one-way ANOVAs? Well, let's try running one so we can see how it all works out. And here, you can run a one-way ANOVA with two groups. And the results are basically the same as a t-test. But typically, ANOVAs, t-tests are for two groups, ANOVAs are for more than two groups. And this example I like because they went with the simplest possible one-way ANOVA, which is just 3 groups. So the example here is they're investigating puppy therapy. I think they said they go to the library. Does anyone remember? They go to the library and give people puppies when they're studying. So you either get no puppy, which would be sad to be in that group, especially if you knew the other groups. Or you get a puppy for 15 minutes, or you get a puppy for 30 minutes. And then when you return the puppy, or after the allocated time, they ask you about your happiness. And we'll assume that this is a continuous scale of sorts that's appropriate for parametric statistics. So here are the data, and let's see. Okay, I'm going to switch to SPSS here. So under analyze, it's still compare means. This is where we went for t-test, and one-way ANOVA is also under here, which maybe hints at the similarities to the analysis. And here, so we can see these are the names of our columns and group. So are you in the control group or 15 or 30 minutes of puppy therapy? That goes into the factor field. And then the dependent variable, what we're measuring is happiness. So we're going to put this in here. We're not going to worry about post-hoc comparisons for this test. We'll look at these later with our next example. Under options, though, we will ask for descriptive statistics. So it gives us means and confidence intervals for our groups. So we'll say continue, paste. Oops, no, we didn't want paste. Sorry. Paste, I often use this, but this gives you the code to actually run it. Sometimes I like to do that to save it for later. Also, we will eventually get into needing to edit the code, but not today. So we'll run this, and we'll go over here. And SPSS, sometimes the output can be very long, but for one-way ANOVAs, it's actually not too crazy. It will be a bit longer when we add in post-hoc tests. But let's go back to PowerPoint just so we can zoom in on these tables. Oh, I forgot to ask for a plot. So if you want to plot, when you go to options, you can say, hey, give me a plot of the means. And then you'll get these 2 boxes. Oh, no, thank you. And you'll get a little plot as well. Not the kind of plot you want to include in the paper, but good for just looking at the pattern in the data. Okay, so here's our plot. We've got happiness over here. The higher, the happier one. And we can see that a control group has the lowest level of happiness. And 50 minutes of puppy therapy, your happiness has increased statistically. I don't know. We'll have to delve deeper. And then with 2, this group is 30 minutes of puppy therapy, and the happiness, at least visibly, is higher. Here's our descriptive statistics. So we can, check, okay, did all of our data get inputted? Yes, we're seeing 5 participants in each group. That's what we expected. We've got our typical descriptives and our confidence intervals. Those, of course, are the standard. They're not difference adjusted. So that's our, we had descriptors used for t-test. The new part is the ANOVA table. So instead of a t-test table, we have an ANOVA table. And we want to look to see our p-value is over here. And just like before, if it's 0.05 or less, then it's significant. So we have a significant result. Instead of a t-value, we have an f-value. And the larger this is, the more likely it is significant. But it depends on the degrees of freedom. And we have 2 degrees of freedom now. We have the degrees of freedom between groups, and we have degrees of freedom within groups. There's also the total degrees of freedom. So how would we report this before we get into what does it mean? So here's the typical way you report an ANOVA. So you have an F value and it's italicized just like a T value would be. The degrees of freedom here is between groups, and then this is within groups. We'll talk about those formulas. You say what that is equal to in terms of the F value. We're rounding to 2 decimal places. P value, italicized P, spaces in here, and then we round this to 2 decimal places as well. You might notice, hey, there's no effect size. My version of SPSS doesn't give me the effect size. I'm curious if your newer version is. We'll look at that today. But we can manually calculate eta squared, which is kind of like cohency. We'll look at that. Here's the formula for degrees of freedom. So for between groups, it's 2 degrees of freedom. How do we get that? Well, you take your number of groups and you subtract 1. So this example had 3 groups, subtract 1, 2 degrees of freedom. So pretty easy calculation there. Within groups is a little bit harder. You take your total number of participants. Here we had 15 participants, 5 in each group, total is 5. And then you subtract the number of groups. So this would be 15 minus 3, which is 12. And that's how we get 12 degrees of freedom. And the total, one way to think about it is literally the between group degrees of freedom plus the within group degrees of freedom. But this one we actually don't report in the statistical results. Checking. All right. So one way to refer to this result here, this significant result in this case, is this is like an omnibus test that says, hey, is there anything significant in here in all of this? And the answer is yes. The omnibus test says, is there anything going on? It says, yes, there is something significant. But we don't know what is significant yet. Is it, is this group different from that one and this one? Are these 2 different from each other? Are those 2 different from each other? We don't know. We just know that there's at least 2 groups or more that are different from each other. So that's all we can tell with our omnibus test. It's not that helpful. We need to now go into some post hoc tests to say, hey, well, which groups are different or not different from each other? And oops, why are there 2s there? Don't know why there are 2s there. That's weird. So let's go back and please ignore the 2s. So if the omnibus test was not significant, if the p-value was greater than 0.05, we could conclude that the 3 groups are comparable to each other. I guess I shouldn't say they're exactly equal because one might be 5, the other might be 5.01, but they're not significantly different or comparable. And we do have a significant F value, so we know that all 3 groups are not comparable, but we don't know which one of these 3 situations it could be. And I guess it could be even more if we didn't already know that the data kind of increases. Because it could be, could have decreased, it could be increased, then decreased, but we saw the visual pattern wasn't increasing. So it's likely one of these 3 patterns. It could be that the first group is smaller than the next group, which is smaller than that group, like significantly so. Or maybe just the first 2 groups are different. or maybe the first and second groups are different from each other. But we don't know. The omnibus test, all it does is answer this question. So we know there's something going on, but to figure out exactly what is going on, we need to do post hoc tests, which are kind of like doing multiple t-tests. We'll come back to those a little bit later. Any questions about the omnibus F-test, the basis of our one-way ANOVA? A little unsatisfying at this point, right? Because all we know is that something is happening. So effect size, we're missing an effect size here. And for a one-way ANOVA, the effect size we use, there's a few options. Not as many as there are for t-tests, but eta squared is probably the most common. And so that's one we'll use. And eta squared, at least in my version of SPSS, is not calculated. I'm curious when you guys do the in-class assignment if it might be like Cohen's d was calculated for y'all. But the formula for it, so eta squared, so this is eta, the Greek symbol squared. And the way you calculate is you take your sum of squares between groups divided by your sum of squares total. The only trick here is, make sure you're using the sum of squares, these two values, and not your mean squares. If you try to use your mean squares, though, there's a mean squares between groups. There's actually no mean square total. So hopefully that, if you try to do that, it'll redirect you to use these values. So I just plug those numbers in, just two numbers to divide for my eta squared. And like Cohen's d, there are kind of thresholds for a general effect size. So here we have a, you could probably call that a very large effect. And that's, again, because this is made up data that is made to be very obvious. A little side note on effect size and one-way ANOVAs. Later, when we do factorial ANOVAs, which I know we haven't done yet, but we'll get to them soon. For those, we actually typically use partial eta squared. And SPSS will actually tell you partial eta squared. So I don't know why it doesn't tell you eta squared, or at least in my version, it doesn't. Now, for a one-way ANOVA and only one-way ANOVAs, eta squared and partial eta squared are actually identical. So this is the formula we'll see for partial eta squared. You can see it's a little different. So it's the same numerator, but the denominator is different, right? We've got these two terms, whereas there it was just sum of squared total. But if we put those numbers in and find the answer, we actually get the exact same number for a one-way ANOVA. For a factorial ANOVA, you will not get the same answer. The reason this occurs for one-way ANOVA is because the sum of squared total, this value, is literally equal to the sum of squared between group plus within group, which is the denominator here. So this is actually the same thing. It's the same formula. That's why you get the exact same value. However, if you're reporting a one-way ANOVA, you always want to call it eta squared. Every once in a while, I'll read a manuscript and they do a one-way ANOVA and they report partial eta squared. And although it's technically the same thing, it's always like, ooh, it always rubs me the wrong way because you should always call it eta squared. I don't know if I have a better explanation for it than that. Even though they're the same, you want to show your statistical savvy in this by reporting eta squared for ANOVAs and typically partial eta squared for factorial ANOVAs. You can actually use eta squared for factorial ANOVAs, but I think there's less support for that, and this is built into SPSS to use partial eta squared. Ooh, the other thing I should mention about eta squared and partial eta squared, you may have noticed that I didn't put a 0 on the front, and that's because eta squared is bound between 0 and 1. And that's different than Cohen's d. Remember, Cohen's d could be, I guess, as big as it wants. There were even standard thresholds for, very large. I can't remember if it was very large, but it can be above 1. Eta squared is a value between 0 and 1. And it's the percent of the variance explained by the groups. So we'll talk more about this in the advanced class, but here we're saying that if we look at all the variance in the data, 46% of it is explained by having these three different groups. There's some other variance in the data that's unexplained by the three different groups, and that could just be that different people react differently to puppy therapy. So we calculated that squared, and then we just added on to the end of our statistic line, similar to how we put colon T at the end for a t-test. Any questions about effect size? All right, let's delve deep into an example where we look at the assumptions and we get into post hoc tests. And we'll have, I think, 5 groups here, so more complex one-way ANOVA. So this is a study I found online that's actually a pretty big study. We looked at the aerobic capacity, so VO2Max, among other things, of 3,860 healthy Norwegian males and females from the ages of 20 to 90 years old. So a very big data set. I do not have the data set. They actually in the manuscript says, hey, you can contact us if you want it, but it wasn't as open as that. Like, hey, I want to use it in my stats class, but I think it was like, you're going to need some justification. Maybe we're going to be co-authors. It kind of sounded more like that. But what I did is I took so we'll look at VO2Max, and they give means. So there's a mean. I'd have to check the caption to see if that's a standard error or standard deviation. But I put that into MATLAB and said, hey, give me data that matches their results. And today what we'll do is I pulled out 5 groups. There weren't a lot of 70-plus-year-olds. It was a small sample size, so they wouldn't be as accurate estimates. And we're going to look at the males today. So we'll have 5 groups: 20-year-olds, so 20, 29, 30, 30-year-olds, 40-year-olds, 50-year-olds, and 60-year-olds. I think when we do factorial ANOVAs, we'll run a more complex analysis with males and females. So what I did is I simulated the data with their mean and standard deviations, and I said, MATLAB, give me 50 participants in each one of those 5 groups, and then we'll run a one-way ANOVA on that. But first, we should talk about the assumptions for one-way ANOVAs. The more complex the statistical test, the harder it is to test the assumptions, and then the harder it is to correct the assumptions. And once we get to factorial ANOVAs, we kind of almost say it's so difficult to even test the assumptions that we're not even going to bother looking at them, which seems odd, especially how diligent we've been at assumptions with t-tests. For one-way ANOVAs, we're kind of at that threshold where we can kind of test them and we can kind of correct them, but it's starting to get iffy. The tests aren't great. They could be underpowered or overpowered. And the corrections aren't great either. They might overcorrect or undercorrect. But some things remain, like we should have continuous data. This is a parametric test. Yep. There shouldn't be outliers. So we could do box and whisker plots to look for outliers. I think we've done that enough on the assignments that we won't do it again. I will show you for these data. Again, the solution is, well, what's normal? Does anyone work with VO2Max data? Does anyone have any suggestions for outliers of VO2Max? I was going to ask Dr. Seifuchi.
It was like in the 60s, that'd be pretty. 60s or 70s.
Starting to get high, right? Very elite.
Yeah, 70s especially.
I think we're on the West Country.
Yeah.
When we look at the data later, I added in a label scheme because I'm not as familiar with VO2Max, but it does show like this is elite, and I think it's like up there in 60s and 70s. And then I think very, very low too, it's like health risk or something like that. Oh, here we go. There, right away. So this is, these are made up data, but so it's the same on your assignments. It's slant. You've seen outliers. It's slant. There are outliers here as well. So you can see, there's very maybe the best Olympic athlete. They fall into elite, and then down here, that's an outlier for 20-year-olds, and that would put them into what do we have, low risk. Doesn't seem that bad. So yeah, we've got a couple of outliers. It's made up data, so not a big deal. But these might be an issue to running the one-way ANOVA. It's not supposed to be outliers. Do we have a great fix for it? No. Can we just get rid of them? Maybe. So again, we're kind of dancing around what to do about outliers. We'll leave them in for now, as we've done in the course. Normality, we can use our typical KS and SW tests to look for a normality in each group. So we could look at those tests for the 20-year-olds, 30-year-olds, 40-year-olds, 50-year-olds. We have 50 participants, so we do need to remember that the tests are overpowered. So if they're not significant, great, we know they're normally distributed. But if they're significant, we don't know, are they not normally distributed, or is the test overpowered? The solution here is a little more complicated than with the t-test. Remember, we could go from, oh, sorry, that's the one. What's the solution for t-test normality issues? We didn't have a solution, did we? Yeah, that was the homogeneity of variance. So I don't think we had a solution. Here, the solution, oh, well, I guess you could do a robust version of a t-test. SPSS won't do that for you, at least not that I know of, but R will, and it's also not straightforward. You could also do that here. You can do a robust version of a one-way ANOVA. So robust means that it can safely handle the violation. And that's a solution here. I guess the t-test, another solution is to switch to a non-parametric test. Yeah, okay, there we go. Non-parametric test, which is never used, but that's what it's called. There's a non-parametric t-test. Does anyone know the non-parametric t-test name? Non-parametric t-test, that's a good name. Or a robust one-way ANOVA. So here are the KS and SW tests, and I guess we're kind of lucky in that nothing is significant and it's overpowered, so we can conclude that all of our each group is normally distributed. If we did have a problem there, though, then that would be okay. Well, what do we do then? Non-parametric test, robust test, outside the scope of this class and my knowledge. Okay, another assumption are that the data or each group has to be independent, and that's not something we can run a test for. That just means that each participant in each group is a different individual. You don't want. Oh, well, that's an interesting question, because like, what if this is a multi-year study and you test someone when they're 59 and then they're 60 because you test them again and they could then fall into the other group? That's a good question. I don't know. Generally, we want our groups to be independent, so maybe you can't do that. That would definitely be like repeated measures. And lastly, like with the t-test, we need equal variance between our groups. And before, remember, if you violated this with t-test, you go from equal variance assumed to equal variance not assumed. There's something similar with the one-way ANOVA. It's in a separate table, you have to actually ask for it in the options menu. But there is a Brown forcent or a Welch correction that we're not going to worry about. I think we will look at the test just once for giggles. Oh, here it is. So the test results come out very similar to the t-test results. So equal variance, or the technical term homogeneity of variance. And we typically look at the significance value based on the mean and based on the median. Here, they're both not significant, suggesting that our groups do have equal variance. Any questions about the assumptions? It's kind of the transition with assumptions where, I mean, you definitely don't want to be using, discrete or non-continuous data, where you don't want to violate independence. But these other things, kind of wave our hands at them and say, okay. There is debate over, well, let's say you have an outlier. How bad is it to include one outlier? Well, is it a huge outlier? What if you have 20 outliers? Well, that would be worse, but how much worse? We don't really know. There's not a good box you can check off in SPSS that says, oh, stop, don't run a one-way ANOVA. Like, we don't know, we don't have a good idea of how good our tests are for violations, and then how well do the corrections work, if we even have a correction. All right, let's run these data. Close this, I don't get confused. And more puppies. Okay, so here are our data. There are 50 participants in each group. So group 0 are the 20-year-olds. And then our last group, group 4, are the 60-year-olds. And here I made sure to put in labels for the group. So instead of just saying, oh, group 0, group 1, it'll actually put nice labels on that make it easier to interpret. So instead of putting 0, 1, 2, 3, 4, it'll say 20-year-olds, 30-year-olds, 40-year-olds, 50-year-olds. Just makes the data a little easier to interpret, especially if you have a data set and then a year later you need to bring it back up and you're like, whoa, what's group 2? So we're going to run a one-way ANOVA, and groups are the factor, and VO2Max, that's our dependent variable. Here we will ask for descriptive statistics. We'll have a test homogeneity of variance. These are the potential corrections to that. We'll ask for a mean plot. And we'll come back to post-hoc tests later. Yeah, I think we do that later. Yes, definitely do that later. Spend a good time on a good deal of time on post-hoc tests. Say okay. And let's go back to SPSS. But here you can see the descriptives. We already saw Levine's statistic for test of homogeneity of variance. There's our ANOVA table. Just off the bat, we can see, yep, something is significant. This is if you need to use a correction for unequal variance. You can see that the degrees of freedom change, and the p-value changes. Although here they're small, so it doesn't look any different. But let's see, this should be a little bit bigger than that one. Okay, so 3.3 times 10 to the minus 22 versus 1.7 times 10 to the minus 27. Yeah, that's smaller, right? Yeah, 22 versus 27. And then there's our plot. So as you would kind of expect, as you get older, your VO2max decreases, or your aerobic intensity is reduced. So, on average, 20-year-olds are better aerobic athletes than 6-year-olds. Not a surprise. But the question is, okay, something is different here. Well, which of these points are different? We're going to need post-hoc tests to tell us, well, what if we compare this group to this group? Is that significant? Is that significant? Is that significant? Is that significant? We don't know. We just know that at least one thing is significantly different. But it could be that all pairwise comparisons are significantly different, or just one, or somewhere in the middle. We've got our confidence intervals. These are standard confidence intervals, not difference adjusted, which are easier to interpret. Oh, yeah, of course it doesn't tell us n squared, so we can calculate it as the sum of squares between divided by sum of squared total. And here it's 0.41, so 41% of the variance in the data can be explained by these 5 age groups. And that's very large. That's likely because two things. One, it's made of data, although it's based on real data. But within that real data, there's a big difference in VO2max over a 40-year lifespan. I mean, it's visible, right? Like if you had a 20-year-old run a race against a 6-year-old, even if they're both as trained as possible, the 20-year-old is probably going to win. So that's why there's a big difference in a big visible difference and a big effect size to VO2Max over the lifespan. It's kind of like saying, can you see a visible difference in the height of a 1-year-old versus a 10-year-old? It's like, yes, that's another huge effect size. So here we're going to report the results. So we, I don't know if that's italicized or not. I'm going to lose marks on my assignments. So our first degree of freedom is 4, or the number of groups minus 1. So 5 minus 1 is 4. The second degree of freedom, this is the total number of participants, which is shown in the previous slide. So there's 50 in each group. There's 5 groups, so we have 250 total. Subtract the number of groups, which is 5, giving us 245 degrees of freedom to the within groups calculations. We put in our F value, we rounded to 2 decimal places, 43.35. Our P value is very small, so we just say P less than 0.01. And head squared, which we just calculated. And here, there should not be a 0 there, because it is bounded between 0 and 1. My APA score is going drastically down. So we know something is happening, but this omnibus F test leaves us quite unsatisfied. We don't know what is happening, so we need post hoc test. Here I've done a bar plot of the groups, and I actually changed the confidence intervals to be different adjusted confidence intervals. So we can use the rule of I here that let's compare 20-year-olds and 30-year-olds. So is the mean of this group within this confidence interval? No. So if we did a t-test, these would be significantly different. The post hoc test we're going to look at, a good post hoc test won't be as powerful as multiple t-tests, because remember, with multiple t-tests, we have a very high family-wise error rate or effective alpha. We need to control that, which will make our test less powerful. But we can kind of get an idea of what we might see. If you look at these two groups, you'll notice that if we ran a t-test on those, they would not be significantly different, because this mean falls within this confidence interval, or vice versa. This mean falls within that confidence interval. But everything else, is visibly, based on rule of I, should be significantly different. Is this group different than this group? Well, yes, because it's just outside of that confidence interval. So let's look at post hoc tests. Has anyone used post hoc tests before? Casey, is there one you often use? Buckrunning? We will look at Buckrunning. Just because you mentioned that. So we will focus on post hoc tests, but I'm going to make a quick comparison to a priori comparisons. So post hoc tests, this means after the fact, you want to potentially compare all the groups. You don't always compare every single group, but beforehand you didn't say, you know what, although we have 5 groups, I only want to compare this one and this one and this one and this one, or some subset of all possible comparisons. So a priori means before the experiment, you decided, I want to do these comparisons. Post hoc means just going into the experiment and say, I'm going to compare everything, or I'm going to potentially compare everything. We'll go over a priori comparisons in the advanced class. They're quite constrained. With a priori, you can't say, I want to compare everything. Well, it'd be nice if you could, but you can only really do that with a post hoc test. So post hoc, not planned in advance, hence post hoc. A priori means it's planned in advance, and you're going to make a subset of comparisons. This is our second one. So green is good, red is, more limiting or somewhat bad. Post hoc, you can compare everything. We call that full pairwise comparison. You can compare 20s to 30s, 20s to 40s, 20s to 50s, 20s to 60s, 30s to 40s, 30s, so on and so forth. With a priori, you can't do that, and typically you can only make k-1 comparisons, k being the number of groups. So here we had 5 groups, so you can only make 4 comparisons. That's quite limited. That may be why we choose not to do a priori comparison. The good thing about a priori comparisons is that the family-wise error rate remains 5% or whatever you set your alpha to be. With post hoc tests, it's not going to be as bad as what we saw earlier with the math to calculate using multiple t-tests, but the family-wise error rate typically is going to sneak above 5%. A priori comparisons, they end up being more powerful than t-tests, which is great. Post hoc comparisons, because we're controlling the family-wise error rate, they end up being less powerful than t-tests, and we'll see that. So we're going to talk about post hoc comparisons, most common by far. Sometimes I use a priori, it's not as often. In SPSS, we have 18 options. And SPS is weird. Once we get to repeated measures, it gives you no options for post hoc tests or one-way ANOVAs, factorial ANOVAs within participant. Sorry, between participants, you get 18 options, which is almost too many. And we'll talk about I think 4. We'll look at the extremes and then the 2 maybe best ones to use. So when you're doing your ANOVA, if you want to do something a priori, it actually falls under contrast. It's another type of a priori comparison. For post hocs, you click on post hocs. And here, in all of its glory, are the 18 options. Now, one thing I failed to mention earlier is the test of equal variance. Remember how if you have equal group sizes, then we don't have to worry about equal variance, and these data are nice because we've got 50 participants in each group. We did look at equal variance, but because there's 50 participants, we don't have to worry about it for the omnibus test. But even with equal numbers of participants, unequal variance can be an issue for the post hoc test. And that's why the post hoc tests are separated into equal variance assumed and equal variance not assumed. So if you have equal groups and you have a violation of homogeneity of variance, then it's probably best to use one of these 4 tests. I think one of them will make a brief appearance later. But for now, we're going to focus on, we're going to assume we have equal variance. And this first one here, LSD stands for least significant difference. I don't know why they call it that, but it is almost exactly the same as running multiple t-tests. So we have very little control of the family-wise error rate here, and the effective alpha, we can calculate that with the formula we saw earlier, and for 5 groups, it would be very large. So you typically don't want to do that because your family-wise error rate will be huge, but the trade-off is that is the most powerful post hoc test you can run. Almost exactly the same as doing multiple t-tests. We'll compare those in a few slides. So here are our 5 groups. These are the means. And we're going to look at the output of the LSD post hoc, or the least significant difference post hoc, which is basically a series of t-tests, all possible t-tests. And the way we interpret them is we start by looking at our mean data. And what we do is we write out our groups. You can do largest to smallest or smallest to largest. I usually stick with the smallest to largest, so that's what we'll do here. So I want to see which of these groups has the smallest mean, and it's our 60-year-olds. So I'll just write 60s to keep it brief. And then this is actually fairly simple data because the means increase with our groups. So we've got 60s, 50s, 40s, 30s, and 20s. So that's how I would write out the data. And we would do the same thing regardless of the type of post hoc test. Oops, okay, here we go, great. Now we want to look at the output of the post hoc test. And here, so it's showing us here are the multiple comparisons. And what is it doing? It's doing LSD, which is almost exactly the same as multiple t-tests. This is a very big table, but several of the tests are repeated in here over and over. I guess every test is in here twice. Okay. So this is the first test. Are 20-year-olds different than 30-year-olds? This is basically the p-value of a t-test. So yes, they're significantly different. What about 20-year-olds and 40-year-olds, 20-year-olds and 50-year-olds, 20-year-olds and 60-year-olds? Yes, yes, yes. They're all significantly different from each other. Now, if you look at this one, this is a repeat of the first one. Here was our 20-year-olds different than 30-year-olds. Well, now we're looking at our 30-year-olds different than 20-year-olds. It's the same thing because it's a two-sided t-test, so it doesn't make a difference. These would be the exact same p-values, even if you click on them and look at them to a million digits. So it looks a bit crazy, but I think every test is in here twice. The way we interpret this is we're going to use this grouping that we created, and we're going to start at one end or the other. We'll start here, just to be consistent, and we're going to look at those comparisons first. So let's go to our 69-year-olds. Here are their 5 comparisons, and we're looking for any comparisons that are not significantly different. So these are actually all significantly different, so we don't have to do anything to our number line over here. Let's go to our next group. That's our 50 to 59-year-olds. Let's look at those 5 comparisons. They're all significantly different, so we don't need to do anything yet. 40 to 49-year-olds. Here are the 5 comparisons. 1, 2, 3, 4, 5. Ooh, we've got our first non-significant result. So 40-year-olds are not significantly different from 30-year-olds. And the way we're going to draw that is we're going to put a line over 40-year-olds and 30-year-olds to denote a non-significant difference. Let's go next to 30-year-olds. 30-year-olds are not significantly different from 40-year-olds. Well, that's a repeated test. We've already captured that in our post hoc summary. I don't know if there's an official name for this. So we're good. 20-year-olds, none of these tests are non-significant. So we have finished summarizing our post hoc tests. And the way you can look at these is you can now say that, well, 60-year-olds, their VO2Max is lower, significantly lower than 50-year-olds. And 50-year-olds are significantly lower than 40-year-olds, 30-year-olds, and 20-year-olds. But when we get to 40 and 30-year-olds, they're actually not significantly different or comparable to each other. And 20-year-olds, they're significantly higher than 30-year-olds, 40-year-olds, 50-year-olds, and 6-year-olds. So here there's really only the one non-significant difference, and that's 40 and 30-year-olds are comparable to 30-year-olds max. This is a fairly easy post hoc analysis. It's not always this easy. And sometimes it doesn't actually work out perfectly. So sometimes you get things that are a little odd, and that might happen on your assignment. So if you get something a little weird, let me know and we could look at it together. With this graph, I flipped it the other way around so it matched our data. So these are our 60-year-olds here. And basically what we're seeing is, yes, this is a significant increase. This is a significant increase. These are comparable, and then this is a significant increase. Has anyone used this before? No, Alan has. So what's the problem with the least significant difference? Well, it's the same problem we talked about with multiple t-tests. And the bad thing is that the family-wise error rate is very high. And here, if you calculate it, I think it's 40%. Hopefully I got that number right. The good thing about it is because there's so many false positives, that means the test conversely is very powerful. So we have the best chance of finding a significant difference or the most number of significant difference. So that's good, but So power, good. Family-wise error rate, really bad. So what would be the exact opposite direction? And that would be, that's actually Bonferroni. Oh, here I was going to make a comment about, is least significant difference exactly the same as multiple t-tests? It's actually not, and I can show you that here. So here are the LSD tests, and these ones all have tiny numbers. So let's just look at the one that had a reasonable p-value. So if we compare, oh, I've gone to my this one doesn't have labels, but I think that's 30-year-olds and 40-year-olds. The p-value is 0.436. If instead we do an independent samples t-test, just say, okay, they're 30 to 40-year-olds, p-value, a little hard to see here, but it's 0.432. So it's not exactly the same. And the reason it's different is because we're assuming equal variances. So if we look at the variance here, which you can look at as standard error way, 1.36. If we look at the standard error over here, for 20 to 30-year-olds, notice it's 1.4. So it's different. And the reason it's different is because it's looked at the variance across all the different groups and pooled them together, which makes sense because we're assuming that every group is equal variance. So instead of doing tests with the actual variance of every individual group, it pulls them together into one omnibus assumption or hypothesis of the variance. And that's why these tests actually are not identical, but the effective alpha is here basically the same as if you're doing multiple t-tests. I want to make those bigger. It's really hard to see. So yeah, mean difference is the same, but the standard error is actually different because it's pooled across all of our groups here. Let's look at Bonferroni. So Bonferroni is going to be the opposite end of the spectrum, where power is horrible, which we want as much power as possible. But the good news is that the effective alpha will be exactly 5% or even lower, better. So we can ask for Bonferroni. How does Bonferroni work? One thing I like about Bonferroni is the math is really straightforward. Is to calculate the alpha that we're going to use for the Bonferroni test. We take the alpha we want to use, typically 0.05, and we divide by the number of comparisons. So if you're doing one comparison, a t-test, it's 0.05 divided by 1, so it's still 0.05. But if you're doing 10 comparisons, the actual alpha that SPSS will use to determine significance is 0.005. So you can imagine it's going to be much harder to find a significant result because your alpha is small. Let's see here. Oh yeah, that example covers us 5 groups, 10 comparisons. That's 4 divided by 2. And basically, if every individual test has an alpha of 0.005, then overall, all the comparisons will have a family-wise error rate of 0.05, or sometimes a touch lower. So Bonferroni does a really good job at controlling the family-wise error rate. This is with no correction, so this is LSD or multiple t-tests. You can see it gets large quite fast. And with, I guess that's not exponential, it's more logarithmic. And then here with Bonferroni, it doesn't matter how many groups, how many comparisons, it will be 0.05. If you zoom in on this, sometimes it actually goes up and down a little bit, but never over 0.05. This is a demonstration of what your Bonferroni alpha will be. So we just talked about the case where we have 5 groups. So your Bonferroni alpha is 0.001. With just 2 groups, the Bonferroni is 0.05. So there's our typical Bonferroni alpha, our typical alpha. Bonferroni, although it's great at controlling the family-wise error rate, it really kills your power. So it's hard to find significance when your alpha is 0.0001, for example. So typically Bonferroni is only suggested if you have 3 groups. You have 2 groups, you're using a t-test, so it doesn't matter. 3 groups, yeah, you can use Bonferroni. 4 groups, your alpha is starting to get so small, and it's such a hit to your power that Bonferroni is not typically suggested. Will you see it used sometimes? Yes. Is it very good in controlling family-wise error rate? Yes, but maybe it's too big a hit to your practice. So here are the results. We get a very similar table, but up here it says, yep, you're doing Bonferroni correction. And what it does is it automatically adjusts all the alpha values so that we can still use a threshold of 0.05. It's done magic in the background, so things have been adjusted to account for the new Bonferroni alpha. But instead of you coming to this table and having to crunch out, by hand, oh, what's Bonferroni alphas here? It's just changed everything so that we can still use this typical threshold of 0.05 unless this is significant. But the numbers have changed, and we can already see that. So remember, this was 0.436 before, or 432. Now it's 1. And we're going to do the same thing we did before. We put out our groups from the smallest mean to the largest mean. We start at one end or the other. So let's start here, 60 to 69. We look for non-significant differences. Everything's significant, so we keep going. 50. Oh, here we go. Here's our first non-significant difference. 50 and 49. 50s and 40-year-olds are not significantly different. So we're going to need a line here for that. Let's go to 40s. Okay, 40s are not significantly different from 30s and 50s. 40s and 50s, well, we don't need another line because we've already captured that. But we're going to add a second line to show that 40-year-olds and 30-year-olds are not significantly different. Let's go to our 30-year-olds. 30-year-olds are not significantly different from 40-year-olds. We already have that with this line. We don't want a single line. We don't want to do this because that would suggest that 30-year-olds and 50-year-olds are not significantly different. But they are. If the results were different, we might want one line, but here we need 2 lines. And then let's get to 20-year-olds. No more not significant differences. So here to explain those results, we need 2 lines. Let's draw those here. And if we look at the data, because we've controlled our family-wise error rate, our tests are less powerful. And that's why we're seeing more things that are not significantly different compared to when we did LSD. So yes, these are the smallest group, or the lowest VO2max. VO2max significantly increases, but then stays the same or is comparable. And then from 40s to 30s, it is comparable, although these two are significantly different. And then this group is significantly higher than that. So Bonferroni is essentially the opposite end, and we're very happy about our controlling of the family-wise error rate, but that aggressive control cuts into our power. And ideally, especially if you've got more than 3 groups, we kind of want something in the middle, where we control family-wise error rate a little bit, and the power is not down too bad. And the 2 tests that are maybe best at doing that are the REGWQ. I think the REGW are all names of researchers who came up with that test, and 2-key test, or 2 keys. Has anyone heard of 2 keys before? Somewhat common. All right. So what I did is, because this is the same data set, I ran almost all of these equal variance assumed tests, ones that at least give us p-values, and I compared them on this chart. And I just chose one test. I chose the 30-year-olds versus 40-year-olds. Yeah, these 2 ones here. And I said, okay, what's the p-value? And because that will tell us something about how much alpha is controlled and how much power has diminished. So alpha with LSD, this is as powerful as it can get, right? It was about 0.436. So there's our p-value. With Bonferroni, we just saw it's actually 1. And what we're going to do is run this on all tests to give us an idea of the power of them. This won't necessarily always be the same because it depends on the data set, but this gives us a representation of what is often found. And first of all, several of these tests, so CDAC, Gabrielle, Hochberg, I don't know if I pronounced those two correctly, they're all very similar to Montroni in that you have very, very low power, but your family-wise error rate is great. So we're kind of at one end of the spectrum, and typically we don't want to live there. On the opposite end of the spectrum, tests that are almost the same as doing multiple t-tests are Duncan and SNK, and of course LSD. So that's, we've gone from this extreme to that extreme, where we don't really want to be either. And the happy middle ground is really two keys or two keys HSD, which is honest significant difference, or the REGWQ. So we'll look at running those two tests. So here are the results for Tukey. And I actually prefer Tukey because, as we've seen for Bonferroni or LSD, you'll get a p-value for every comparison, all of the pairwise comparisons, I guess 10 comparisons in this case. Whereas when we look at REGWQ, you only get, it only shows you p-values that are not significant. So it's a little more challenging to report. You can't actually report a significant p-value. You can only talk about the non-significant ones. So here's our data again. Let's draw some lines. And here's our 60-year-olds, all significant differences. 50-year-olds, all significant still. 40-year-olds are comparable to 30-year-olds. 30-year-olds are compared to 40-year-olds. Already got it. 20-year-olds are significantly different from everyone else. So this is how the data works on this case. More powerful or more significant differences than Bonferroni. That won't always be the case, but generally your p-values would be smaller with two keys than with Bonferroni because it's more powerful. If you run Tukey or REGWQ, there's a second table you get, and sometimes this might help interpret what's happening with your data. It's presenting results in a different way. And for REGWQ, this is actually the only table you get. You don't get that table with all the pairwise comparisons. But if you look at what they've done here, or what this table shows you, is they've actually ordered the groups from smallest mean to largest mean here, kind of like what we did over there, but they've done it vertically. And then they put them in individual columns if they're significantly different. So here they're saying, hey, 6-year-olds, they're significantly different from everyone. 50-year-olds, they're significantly different from these groups and this group. You know, they're larger than this group, smaller than these groups. And then they say, hey, there's another group that includes 40-year-olds and 30-year-olds, and they put them in this same column or group because they're comparable. They're not significantly different. And the p-value for that is 0.936, which we did see in the previous table. 0.936. But notice it is not giving you all these significant p-values. For Tukey's, you can get them from that chart. For REGWQ, that chart doesn't exist. So REGWQ, we can actually see we get the exact same results, but the p-values are different. And in this case, it looks like it's a more powerful test because the p-value for this exact same comparison is smaller. So what would you do if you're doing a one-way ANOVA and you have to pick a post-hoc test? Well, you shouldn't do LSD because there's no correction to the family-wise error rate. If you have 3 groups, you could do Bonferroni. And if you have more groups than that, it's actually suggested or legitimate to run both Tukey and REGWQ. Now you can't just cherry pick the results. You can't say, I prefer this one to this one. You have to go with whichever one is more powerful. And that hopefully there's an equivalent test where you can see which one has a smaller p-value. So in this case, in the method section, we might say, hey, we're going to try running both of these. We'll go whichever one is more powerful. In this case, it's REGWQ, so you have to report that p-value. I typically just stick with 2 keys because I like to have that whole table of pairwise comparisons. Where you don't get that with RGW. So even though these are less powerful than LSD, we actually end up with the same overall results here. But it could be different just depending on the data set. Any questions about our deep dive in the post hoc test? Important caveat. I don't think this will be the case in the assignment because I tried to make in class or at home, I tried to make sure your data had some large differences in them. I don't know if every group will be significant, but at least I think everyone's omnibus F value will be. But in the real world, the omnibus F test is going to be more powerful than the post hoc test, as long as you're not using LSD. Because here, there's going to be a correction for your family-wise error. So what can happen is you can have a significant F test, and then you run your post hoc test, and all of them are not significant. And then that can be a little frustrating. So, well, the omnibus test says something's happening. The post hoc test say nothing's happening. So when this happens, what I do is I look for one or more comparisons that have the smallest p-value. And I'll tentatively say that, oh, well, there's a significant omnibus test, the post hocs weren't significant, but this is the area that was at the lowest p-values. I have an example of that from 2 years ago, where I accidentally, back then we didn't have individual data on the assignments, so the entire class was using the same data, and there were not significant differences in any of the post hoc tests, which was, we hadn't talked about it in advance, so it was a bit confusing. But here are those data. So we have a one-way ANOVA that we were running on these 4 groups. It's reaction time data. And if we look at the omnibus F test, it is significant, not a huge effect size. Might be medium, can't figure it out. But yes, it's saying something is significant. So okay, let's do post hoc tests. Which ones are we doing here? 2 keys. And you can see here that they are all not significant. So it's like, oh crap. But what we can do is say, okay, well, which ones are closest to being significant? And let's see here. This is close to alpha, 0.05, 0.07. So group 0 is almost different from group 2 and 3. So group 0 is almost different from groups 2 and 3, which kind of matches the visuals. What about group 1? Well, group 1 is almost different from group 2 and 3. P-values are a little bit bigger here. So the way I would tentatively explain these results is I would say, hey, there's a significant F test. Here it is. Hey, post hoc tests, all were not significant, but the closest, well, I would say this because you don't want to say approaching significance, but the smallest p-values were when we compared groups 0 and 1 to groups 2 and 3. And that matches the visual as well. But you wouldn't say they are significantly different. You just say, well, those are the ones that have the smallest p-values. This happens more often than you would like. Yeah, if we drew the results, it would look like that. So here we've got, group 0 smallest mean, then 1, then 3, then 4. And if we look at, if we start 0 on the left, well, 0 is not significant. 1, 2, and 3. So we need a line that goes over all of them. But if we talk about, well, what are the visual patterns? What are the smallest p-values? I would draw it as like this. Yes. So some of the post hoc tests are robust or more robust to violations. The textbook talks a bit about this. But if you have small differences in sample sizes, maybe one group has 50, the other group has 60, small difference, then you might want to use the Gabriel test. If you have a large difference in sample size, one group has 10, one group has 100, this test is more robust to that situation. And then, worse violations like unequal variance, unequal sample size, or both, that's when you might want to jump down to equivariance, not assume these are being Howell tests. I actually don't have any experience with those, but that's recommendations from the text. Okay. So let's just look at a summary here. So the family-wise error rate of the omnibus test or of the F test is alpha, so 0.05%. That does not apply to our post-hoc comparisons. So we need to do some sort of correction. LSD is not recommended because it's essentially not correcting the family-wise error rate. Bonferroni is not recommended typically if you have more than 3 groups because it's overly aggressive. Although if you want to ensure a family-wise error rate of 5%, then you might decide to use it even if you have more than 3 groups. And the two that are kind of the best balance are GWQ and Tukey. And it is permitted to run both. So I often just run Tukey because I prefer it, but you can run both and then use the one that is more powerful. A reviewer might get mad at you, and then you might have to ask me for a citation from an actual statistician that says you can do that. They might still be unhappy, but so you can't run both and then go with the one you prefer. But you can go with the one that's more powerful, or you must go with the one that's more powerful. Okay, finally, last topic here. Let's just look at how we would report this in a manuscript. So 2 sections, of course, the method section. This is pretty similar to what we've seen with t-tests. So a one-way ANOVA was used to compare the VO2Max to 5 groups, and I added the 5 groups. That might be redundant if, just earlier you described the 5 groups already. Effect size was reported using eta squared. Reported values were means and 95% difference confidence intervals. In a few assignments, I think almost everyone said, "Hey, I'm gonna report this," except for paired samples. That's where most people did the difference. And some people said, "I'm going to use difference adjusted," and then they use the standard confidence interval, so they don't mark for that. The significant one-way ANOVA was analyzed with post-hoc comparisons, and Tukey's test was used to control the family-wise error rate. What gets more complicated is the results, and these results are not well written because there are so many groups. It's really asking for a figure or a table. But I tried to do an example if I did it all in text. So the one-way ANOVA comparing VO2Max to 5 groups was significant. So that's often how we start things off. And then now these are the results of the post-hoc test. And our post-hoc test, I think this was our result with 2. Well, that's fairly straightforward, and yet we've got a ton of text. And what might be better is to say, hey, look at figure 2, and they're all significantly different except 30 and 40-year-olds are compared. That would be a lot less wordy. But the 20-year-old group had the highest VO2Max, and here because there's a p-value for 20 versus 30, 40, 50s, and 60s. What I did is I instead of reporting all 1, 2, 3, 4 p-values, I just grouped them all together and said p's plural, p's, and they all are actually less than 0.01. If they weren't, you would have to say they're less than and then put in your highest p-value. The VO2Maxes of the 30 and 30-year-olds and 40-year-olds, which I report, were not significantly different. I report that p-value of this comparison. VO2Max was significantly lower for 50-year-olds. I report the p-values for these 3 comparisons, and the largest one was 0.04, so I say less than 0.04. The 60 to 69 group had the lowest VO2Max, and then again, there's 4 p's involved with that, so p's plural, and the largest one was 0.02. It probably wouldn't be that bad, the wording, if I didn't have all of these values, so I took those out, it would be quite a bit cleaner. You could say, table 1, look at those values, or figure 1. If instead I want to use REGWQ, if I had run both and it was more powerful, the text is largely the same. The only thing is I don't have all those significant p-values. They don't exist with RGWQ. So when I say the 28 to 29 year group with the highest VO2 max, before I said p is less than 0.01, I don't have those values now. We just know that they're significant. I guess you could write p's less than or equal to 0.05. That's a safe assumption. And then the only p-value we do have are when they're not significantly different. So I just changed this to the actual p-value from RHWQ, which was a little bit smaller than the p-value with 2, because it was more powerful. Any questions about family-wise error rate? Any? Wrong. That was a whirlwind. Yes, ma'am.
Well, is that a question for that example, that real world example? So there was significance
Yes.
in the one-way ANOVA,
Yeah.
but there was no significance in the 2-key. Like
Yep.
how would you like write that
Sure.
or like mention it in the paper?
Sure. So I would start with, there was a, the one-way ANOVA was significant, comma, here are the stats. And then I would say, all pairwise comparisons were not significant. And I would probably say P's greater than, and I would give the smallest p-value, which is 0.055. Because if I say plural, then that's the smallest. Well, that one's bigger, that's bigger, that's bigger, that's bigger. And then I would go into my tentative explanation. I'd say, well, the smallest p-values were when groups 0 and 1 were compared to groups 2 and 3. And if you want, you could actually report some of those values. You could say 0.055. And I would say that suggests that the main effect was caused by a potential difference in these two groups compared to those two groups. So you got to use softer language. You don't want to say significant, not significant, but you want to say like smallest p-values and suggests, things like that. Okay. Awesome. So for the in-class assignments, I tried to kind of stick with the things that were a challenge on the last assignment and what I've seen are challenging in the past. So you'll run a one-way ANOVA, of course. You have to calculate S squared. Let me know if SPSS does that for you. Then I'd like to see you calculate your difference adjusted confidence intervals, because some people had trouble with that in the last assignment. And then post-hoc comparisons can be challenging. So you'll use the method we looked at in class. So you'll order your groups from an increasing mean. And then I'd like to actually have you run 2-key and then try to write some sentences. You don't have to write the whole results section, but try to explain your post-hoc results so I can give you some feedback on that.